So here we've got our test circuit. Here's our 0.1 microfarad capacitor. There's our 1K resistor, and these are two 15 ohm resistors, which in this circuit are necessary to develop a voltage across each one to determine the current flowing down through the capacitor branch of the circuit and through the resistor branch of the circuit. This is of course the AC RC parallel circuit, and I'm running with 900 Hertz as an input frequency, and we'll have a closer look at the input voltage shortly. I think it's around about 5 volts. Here's the oscilloscope, and the oscilloscope I've already got set up, but what I'm going to do is very quickly take it back to auto by pushing the auto button. These digital oscilloscopes, they're beautiful to work with. Once we go back to auto, of course, the oscilloscope has adjusted itself to display channel A and channel B, or channel 1 and channel 2. And that's not really the way I want to see the waveforms today. What I want to do, I want to use the position control. I want to move channel 2 up to the middle of the screen, look for that detent position there. Channel 1, I can move that down to the middle, and now I can see that I've got a time difference between the two waveforms. And this is so important to understand, that the capacitor current is always at a peak when the voltage across the capacitor is 0. And when the voltage across the capacitor reaches the supply voltage, the capacitor current drops to 0. So with a sine wave, they're always 90 degrees out of phase.
You know, there's something about this little capacitor. It's very similar to this tyre on my car. When the capacitor has no charge in it and voltage is first applied, a lot of current has to flow in to charge up that capacitor. Just like my car tyre. My car tyre is a little bit flat, and I'm going to put some air into it. And while the air's going in, at a rapid rate. A lot of current of air is flowing because the tyre is flat and the compressor has more pressure than what the tyre does have. But once the tyre equals the set pressure at 34 psi, then no more air flow takes place. No more current of air takes place. Then the current of air which is flowing from the compressor rapidly reduces because they equalise, and then there'll be no more air flowing. And it's just like this capacitor. Like I said, the little capacitor charges up. It starts with no charge, and a lot of electric current has to flow in to charge it up, and then when it reaches equilibrium with the supply voltage, no more current flows. And what about potential? When it's got no charge, there's no voltage, there's no potential across this capacitor. But after a lot of current flows in and it equalizes with the supply, then we have a lot of potential across the capacitor. Just like the tyre. When the tyre was flat, it hasn't got the potential to drive me anywhere, but when the tyre's fully charged, then I've got potential. When the tyre was flat, no potential energy. I can't drive anywhere. I think it's a good analogy. I'm going to use this analogy for capacitors more and more because it's so important to understand why current flows at a maximum rate when there's no voltage in the capacitor, but then when the voltage in the capacitor is equal to the supply voltage, no more current flows. Same as the tyre. Once the air pressure in the tyre equals the air pressure in the compressor, no more current of air flows. And I've got full potential on the tyre. I love it.
So with a sine wave, they're always 90 degrees out of phase. Channel 1 is measuring the resistor. Channel 2 is measuring the capacitor. Now, this is still really not exactly what would be best to measure these. I could probably increase the sensitivity here a little bit. Now, here's an interesting phenomenon. Because oscilloscopes are set for like 125, 125 multiples, and I go from at the moment on channel 1, I think we've got this set for, channel 1, yes, on 50 millivolts per division. The next setting jumps down to 20 millivolts in that 521, and it's off the scale. Now if I still want to be able to display that waveform and not have it off the screen, I can just bump that scale control, and that puts it into a vernier, and I can bring it back down, and just 28 millivolts per division. That would be 28 millivolts peak to peak, of course. Now the little bit of jumping that I had there on the screen before, which I can control with the level control generally on the trigger setting on the oscilloscope, but if I still have difficulty with that, I'd go into the setup, and I'd go into the coupling, and I'd take it off DC coupling and put it into HF reject. I've done this on a few videos before. It takes a lot of noise away from the input circuitry of the oscilloscope and stabilises the trace, so it no longer jumps with that synchronisation there. Channel 2, selecting channel 2, it's also centered over the center of the screen, and we can do the same thing. We can increase channel 2. Now what I have done, I've used the measure function on the oscilloscope today, and instead of going on the gradicules on the screen and measuring peak to peak, dividing it by 2, multiplying by 0.707, I know I've said in the past, don't always rely on these numbers that the oscilloscope gives us. Here it's saying 72 millivolts RMS for channel 1 in the yellow, 43.6 millivolts RMS for channel 2 in the blue. It could be out by a couple of percent, won't be out by a great deal. They're the values that I'm going to log down for this first part of the practical, and then they're the values that I'll do the mathematics on. So I'll go ahead and do that. I've got channel 1. Channel 1 is the resistor. So I'll just draw a bit of a resistor there. And channel 1, we've got an RMS voltage of 72.1 millivolts RMS. Don't know why I put the 0.1 really, because in past experience shows me it's anywhere probably between about 67 and 75. Channel 2 is the capacitor side of the circuit, and channel 2 I've got 43, I'll put what it says on the screen, 43.6 millivolts RMS. And then the one thing which is missing, which I have not measured so far, is the input coming from the signal generator across into my test circuit. And to do that, if I had a 3-trace oscilloscope, that'd be ideal, but I do not have the 3-trace oscilloscope here, so I'll just temporarily disconnect channel 1 from these resistors, and I'll move channel 1 to look at my input side of that resistor. And of course we're way off the screen, and we can't use the automatic measuring facility as soon as we go off the screen, so we have to whoops, on channel 1 notch him back a little bit. And now he's still in the vernier control, and I'd be going forever to go at 1 millivolt per click on the vernier to get that back, so I'll just bump that and then we can bring it back using the 125. And 4.9 volts, it's in RMS. Good. So the input to my circuit, VN is 4.9, 4.90 volts RMS. And they're the figures that we're going to be doing the work on. Now that I've taken those, it's time to go away and think about the mathematics for this circuit. And then what I'll do, I'll take some snapshots of the screen, add them to the maths, and just see how things stack up.